So again, this is not an exhaustive list. Mass spectrometers are very diverse depending on the type of analyte that you're attempting to separate and measure. But I'll list some of the more common ones. The one that I talked about in the first video was a magnetic sector instrument, and that's really what set the field in motion. That used an actual solid bore magnet with a constant magnetic field. Those are great, they do great things, but they're difficult to maintain, they've got a big footprint, and they've been largely phased out. I've never actually used one personally, but I've used all of these other versions. The most common, cheapest, most robust system is the Quadrupole system, and we have lots of these on campus. And so I'll give you a little bit more description of that going forward. There's also time of flight instruments which operate on a separate principle. And then there are these things called ion traps and orbit traps. There are cyclotrons. There are ion mobility systems. There's lots and lots of different systems out there that get more exotic, more expensive, more niche, but they're wonderful tools if you've got a really specific question that you need to answer. So we're going to start off with the Quadrupole, and as I mentioned, we've got lots of these on campus. It's pretty small. So this is actually a version of the Waters Quadrupole. We have a Waters Quadrupole on our LCMS. And it looks like this. It's about the size of a human fist, and you can see the origin of its name. You have the four rods or the four poles. Each of these four poles is made contact to both a DC and an AC voltage. And what we're going to do to this quadrupole is bias it in such a way with both a static constant direct voltage as well as an alternating voltage at a particular frequency, such that we induce an electromagnetic field on the inside between these four rods. The ions then, these positive ions, are then going to pass between these four rods, but now instead of having this Bohr magnet that had a fixed magnetic field, you have four rods with an induced electromagnetic field where in any given moment in time we can change the voltage to the system or the frequency at which it's being applied, and we can alter the trajectory such that only one possible mass to charge ratio can pass through this unadulterated to the other side, which there will be a detector. Everything else will have unstable trajectories, spiral out of control, and strike the rods. And we can cycle through that many, many times a second, so that we, over the course of maybe 1 second, we started at anything with a mass to charge of 1, all the way up to maybe 400, and we cycle that through several times a second. So we're collecting full spectra and counting all the ions that are able to pass through with stable trajectories. The key here is knowing at what applied voltages correspond to certain masses. We don't have to do any of that. That was all done with the physics that went into designing these tools. In terms of software, all we need to do is just say we want to collect data over this mass spectral range, or we want to only count ions at this one particular mass to charge or over this small range. That's it. So let me show you how this works. So I'll talk over. So those are the four rods. If you're looking down the rods, and you can see applying a radio frequency potential as a function of time between about plus 5,000 and minus 5,000 volts. And this is the simulation of what that field or that potential surface is going to look like as it oscillates between those four rods. So here are our ions moving through the four rods as they're being pulsed positive, negative at radio frequency. Here's another one, and you can see that there are less stable trajectories of the orange one, there are less stable trajectories of the pink one. The only stable trajectory at that moment in time when that potential is being applied is the blue one. And so over time, we're cycling between, so this is at one particular voltage, and we can change that bias then such that we stabilize the orange and count it, and then change the bias such that we stabilize the pink and count it, and we do that tens to hundreds of times a second, depending on how we want to sample and how long we want to dwell, etc. There's a lot of permutations that we don't need to discuss here, but that's the general functional principle of a quadrupole. So as I mentioned before, mass spectrometers are the cheapest out there because they're really pretty simple to manufacture and they're pretty simple to operate. This is just a schematic showing both the ionization source, an electron ionization source here on the front end, and that coupled directly to the quadrupole system here. So these things necessitate high vacuum. Why? Well, as you could imagine, if you had a bunch of stuff filled inside of this quadrupole, then you would no longer be able to really simply separate the resonant ions, those that are in resonant frequency with whatever's being applied, with those that are non-resonant, because they'd be constantly colliding and losing energy with all the other junk that's in the system. That said, there are a variety of quadrupoles out there that exist inside these chambers called dynamic reaction cells, where you intentionally bleed in a particular gas with the intention of actually reacting it and changing its mass and maybe affecting interference species. So if you have an interference species that's really similar in mass to the thing you want to measure, this is especially true for inorganics, then you can bleed in a particular gas like methane or ammonia inside of the actual quadrupole sector, and as long as there's selective reactivity with one of those species, it changes its mass, it becomes aresonant or non-resonant in this case, and it flies or spirals out of control. So not to say it's always under high vacuum, but often. The other sort of downside of a system like this is that the resolution that you have between mass to charge units is about 1, which means you can differentiate roughly the difference between, you know, a single mass to charge unit, which isn't always great if you have compounds that are nominally the same, or if you have isotopes that you know, have a fraction of a mass to charge ratio different from what you're trying to measure. And that's really true for lots of applications out there, but for things like organic molecule analysis, quadrupoles are super robust for just general routine LCMS, GCMS, and a variety of other sort of tandem techniques like that. So the second type of mass analyzer that's pretty common is this thing called a time of flight, or TOF, T-O-F. People call them TOFs quite often. And they operate based on a very different principle. You still have to get your ion into a charged state, so you've got to have some sort of ion source on the front end to get your neutral into a charged state so that it can, again, interact with some sort of magnetic or electrostatic system. In this case, it's electrostatic. And so what you have are ions that come in. So you have this source region that's over here, and you have your ions that are, or your neutrals coming in, they're ionized. And then they enter this called drift region, or first drift region. And this, there's a giant electrode here called the repeller plate. Not many people call it the back plate. It's often called the repeller electrode, and it's biased at a positive voltage. So you've got this electrostatic potential, large and positive right here with respect to ground here. And what that does is these neutrals get ionized, they then are positive, and they're positive here, and you have this large repulsive positive electrostatic force that pushes them into this drift region. That's really what they do, is just drift. And so there's a long tube here which allows the ions to drift. When you take different ions that have different sizes and different mass to charge ratios, and you apply a fixed positive voltage to them, or positive force in this dimension, you can imagine they're going to impart to that some velocity inside of this. This is a vacuum chamber. And the faster ions are going to be those that are smaller. And those things are going to move and zip through at a much faster rate than do the slower, heavier, clunkier ones. And so in this drift region, the smaller ions move faster, and they move all the way till they hit this set of ring electrodes all the way out here, and the ring electrodes are going to sort of slow down and bend the trajectory of the ions back the other direction, and in doing so they augment the trajectory. And this sort of is like an electrostatic monochromator for mass, the sort of way I think about it, because it takes what you have where all these ions that start at the same point in time, and as the slow, or the two drift apart in the drift region based on mass to charge, then when they're applied by the differential voltages across these ring electrodes, they'll sort of penetrate further and further into this series of ring electrodes, and then as they swing back around, they hit different regions of this detector here, or we have a grid here that can allow only certain bands or certain ions of certain mass to charge ranges to pass through at any given moment in time. And so the principle is very different. Instead of using sort of a radio frequency electrostatic potential applied between 4 rods to to change the stable trajectory of an ion. Here we're really allowing everything to go through, but they're going through at different rates based on that original sort of push that they get from the repeller electrode. They penetrate further into the set of ring electrodes or less far depending on their mass to charge, and they disperse into sort of a staggered series of ions that strike the detector, and that's the basis of how this type of time-of-flight mass analyzer works. The good part about this is it's a pretty simple instrument, and it's pretty cheap, and it's good for heavier ions, better than quadrupoles. So we can push above. Quadrupoles are pretty good up to 400 or 500 mass to charge ratio before it gets a little difficult to stabilize ions, at least if you're trying to also include the low range too. And if you have a time of flight instrument, you can start to push the upper bound of your mass analyzer. The problem with time of flight instruments is they're based on this fact that because you're applying the same voltage to all the ions, the kinetic energy of all these ions is the same, at least as it enters here. And that the separation then is based on, if kinetic energy is 1/2 mv squared, then the separation occurs based on the differences in the mass here. But it's difficult to impart exactly equivalent kinetic energies to all these systems. They can collide with each other, and so what happens is the resolving power, that delta mass to charge, the ability to differentiate, is higher typically than a quadrupole. And so they're simple, they're pretty easy to use. But they have a little bit less resolving power, but they are good for heavier objects. So if you're trying to resolve subtle or smaller differences in mass to charge in your ions, time of flight's not great for you. But if you're just weighing bigger, heavier, clunkier things, and you don't really care about the resolving power, at least down to the same level as you would with a quadrupole, then this is a good choice.